Before going to full wave bridge rectifier, we will also have another full wave rectifier, that is nothing but the center tapped full wave rectifier. Actually, if you observe these two, full wave bridge rectifier have 4 switching diodes, but in center tapped we have only 2 diodes. But why we still prefer only bridge rectifier? Why? Because in center tapped full wave rectifier, if you see the transformer, this is the transformer, right? If you see the bridge rectifier, this is the transformer. This is normal step down transformer, but it is not a normal step down transformer. It is center tapped transformer. Okay, center tapped transformer. So when compared to these two, center tapped transformer have more cost when compared to this normal step down transformer. So that's why we prefer only bridge rectifier. And also peak inverse voltage also differ between these two. Okay, that's why we prefer only full wave bridge rectifier. So without wasting time, let's get into the full wave bridge rectifier video. Full wave bridge rectifier. Here rectifier means what? It converts AC to near to DC, not pure DC. Means here input is AC and output is DC, right? I am taking the AC input like this. Okay, some Vs, nothing but the source voltage, like Vm sin omega t. This is the sine input voltage I am taking, nothing but the sinusoidal input voltage. Okay, so nothing but the AC. Let's see how input voltage will be. Okay, if you see the waveform, this is the AC waveform, right? Like some is positive, some value is negative, and then again positive and again negative. This is the input voltage what we have. Just divide by 2 pi, 3 pi and then 4 pi. This is the input voltage, nothing but the source voltage what we have, like this. Okay, here two cycles we will observe. Okay, that is the during 0 to pi, okay, it is the positive, right? And during pi to 2 pi it is negative, and then again positive and then negative. So let's observe during these two, 0 to pi, what will happen? Here only positive waveform will be flowing, means current will flow to the positive to negative. So flow is like this. Just observe. So here we have one diode, that is nothing but the D1, let us assume, and it is go to the load. Take any load, nothing but the resistance I am taking, RL. So this is the load. This is going through the diode D2. So it will somewhere like this. Okay, and again it is a closed circuit. Whenever it is closed circuit, then current will be flowing from positive to negative, right? So here output voltage is input voltage, nothing but the source voltage, because here I am neglecting the losses D1 and D2. So here I am neglecting losses, then only we are getting the V0 is equal to V source, nothing but the input voltage I am getting. That is the operation of when D1 is, D2 is on, nothing but the positive half cycle. So what will happen during negative half cycle? Let we will see. Okay, this is the negative half cycle. Okay, means negative to positive. Okay, negative to positive. So here flow will be like this. Okay, it will goes like this and then goes to diode D3. Okay, and again it will be go to load and it is flow through like this, and here we have somewhat diode and flow like this. So this is the closed part. This is the diode D4. So during negative half cycle also we have closed path, means here diode D3 and D4 is on, but source terminals are reversed. Okay, negative to positive, and then here flow is from negative to positive. So that's why we are also having V0 is equal to Vs, because terminals are reversed, means negative. Here negative will be changed to the positive. Why? Because flow of the current is changed. So that's why I am having the Vs, positive Vs. Let's observe somewhat clearly. So during positive half cycle means this is okay. So means output input voltage is positive Vs. Okay, so here positive to negative is flowing, voltage current is flowing from positive to D1 and then load and then D2 and then negative. Here output voltage is input voltage like positive Vs. Okay, but during negative half cycle, input voltage is negative, right? Negative Vs, not positive Vs, negative voltage source. Okay, so here current will be flowing like this. Okay, like D3 and then again load and then again D4, and it is closed path. So means we are getting the V0 is equal to negative of Vs. Okay, means Vs is also minus Vs. Okay, that's why you are getting the minus of minus Vs, that is nothing but the positive Vs. So that's why our waveform will be negative to the positive. So let's see how output voltage will be. Okay, so output voltage will be during D1 and D2 we are getting the Vs, right? Nothing but the source voltage. During D3 and D4 is on, we are also getting the positive Vs. Again this is the D1 and D2 condition, right? Because of the positive waveform. So here also I am getting the input voltage and then again input voltage positive. So this is the output voltage, okay, output voltage of our full wave rectifier. So that's why it is named as a full wave, because here our waveform will be full wave, okay. Unlike half wave rectifier, we are not getting the positive and zero and positive and zero. We are always getting the voltage, okay. So this is the full wave bridge rectifier operation, okay. Don't need to confuse. So till now we are just seeing the current voltage only, like V source voltage and then V output voltage. Then what about the current? So current will be here, current in the R load have the same phase angle but different amplitude, okay. So let's see how current is. So if you take the input source voltage, then this is the input source current, okay. This will be like this, okay, same phase angle but somewhat amplitude will be changed, okay, like this. So during output also we are having the same magnitude, same phase angle, sorry, but different magnitude, nothing but the amplitude, okay, like this. This is the output current, so this is the source current, okay. That's it. This is the our waveform operations. Don't by heart anything, okay. During D1 and D2, diode D1 and D2 is on output voltage is like input voltage, that's why the black term like this, okay, input voltage. So during negative half cycle also flow is like through D3 and load and again D4. Here low source terminals are reversed, that's why I'm getting the Vs, that's why I'm getting the waveform like this, okay. So this is the basic operation conditions and waveforms, okay. And we can also write a source current Is as Vs by R, okay, nothing but the V is equal to R, like this I'm writing like this. So here also I'm taking I0 is equal to V naught by R. So here in the waveform, output waveform, this is pi, right, 2 pi, 3 pi and then 4 pi. Now let's see the average value of output voltage, nothing but the load voltage is. So I'm taking the V average, this indicates, okay. So here V average is equal to, so let's observe this figure, okay, this output voltage, okay, not current, just only observe the output voltage waveform, okay. This is the output voltage waveform. So here and same thing repeat here also, and same waveform repeating here also. Just take the complete cycle. Here from 0 to pi only it is complete cycle, and again this cycle is repeating from pi to 2 pi, and here also same cycle is repeating to 2 pi to 3 pi. So just take only one is repeating, okay. Just take only this complete cycle 1 by pi. So why I am taking 1 by pi? This is the complete cycle, okay. So I am also take 0 to pi only. So here V source into d omega t. So what is V source? We also know V source is equal to Vm sin omega t. That is equal to 1 by pi into 0 to pi Vm sin omega t d omega t. Now let's solve 1 by t. So let's take constant. What is the integration of sin omega t? Minus cos omega t. Upper limit minus lower limit minus cos omega t plus minus of minus plus cos 0. So cos pi is minus 1 and cos 0 is 1, that is equal to 2 Vm by pi. So this is the V average, okay. That is the average voltage we are having of full wave rectifier is 2 Vm by pi. Now let's see average current, okay. What is the average current? I'm assuming as I average. So we already know V average is equal to 2 Vm by pi. How to calculate V average? We also know I is equal to V by R, right? So here what is V average? 2 Vm by pi. 2 Vm by pi into, just take R. R is nothing but the load resistance RL. This is the average current what we have. Now let's find out the power, okay. The average power. If you take P average, we know V average and I average. By multiplying these two, we are getting the power of average, okay, average power. That is nothing but the V average is equal to 2 Vm by pi. I average is equal to 2 Vm by pi into RL. So that is nothing but the V average square by R. How this will come is, you know, I average is equal to V average by R, right? That's why I am taking the V average square by R. This is the average power. Now let's see RMS value, okay. RMS is nothing but the root mean square value. That is equal to same waveform. We observe this waveform, okay. Here same cycle is repeating from 0 to pi only, okay. 0 to pi only same cycle is repeating. So just take one complete cycle. So here I'm getting the VRMS nothing but the root mean square value. So nothing but the root of, okay, root of what is the complete cycle? Pi, 0 to pi, right? So I'm taking the 1 by pi, again 0 to pi, and then V square of d omega t, because it is the root mean square value. That's why I'm taking the root here. I'm taking the square way here. Vs is nothing but the Vm sin omega t, right? So I'm getting the waveform like this. Root of 1 by pi, 0 to pi, sin Vm sin omega t whole square into d omega t. So here take the constant. So 1 by pi. So here Vm is constant, right? So I'm taking this out. So Vm square by pi. So integration of 0 to pi sin square omega t, right? 0 to pi, what remaining? Sin square omega t is remaining, right? So sin square omega t into d omega t. So by using half angle formula, here I am using the half angle formula. What we are getting? So that is equal to Vm square by 0 to pi. I am writing sin square omega t as 1 by 2 1 minus cos 2 omega t. By using half angle formula, I am writing this. Okay, that's it, into d omega t. Here I am taking the Vm square pi of, so I am taking constant out, pi minus 0 minus pi minus 0. Integration of cos omega t is sin omega t by 2. Okay, sin 2 omega t by 2. So here I am applying the limits 0 to pi. I am taking Vm square of pi 1 by 2 pi minus sin 2 pi. Okay, I am applying sin 2 pi minus sin 0. So sin 2 pi is 0 and sin 0 is 0. So that is nothing but the 0 root of, right? Pi is cancelled and I am getting the only Vm by root 2. So this is the Vrms value. Okay, this is the answer of Vrms. Okay, so we know Vrms. How to calculate Irms? We know the formula. Irms is equal to Vrms by RL. That is nothing but the Vm by root 2 into R. Why? Because this is the Vrms, right? Now let's find out the power RMS. Prms is equal to Vrms into Irms. We write the Irms as Vrms by R, right? That is equal to V square RMS by R. That's it. This is the power formula. Okay, now let's see what is the form factor. Okay, form factor of our full wave bridge rectifier. So form factor is nothing but the ratio of RMS value to the average value, V average. We know the RMS value. RMS value nothing but Vm by root 2. Here we are already calculated. V average is nothing but this one. This is the V average. First term we are calculating. Okay, V average is equal to 2 Vm by pi. Okay, now let's see. Vrms is nothing but the Vm by root 2 into V average is nothing but the this one, 2 Vm by pi. Now I am taking this one. Okay, pi by 2 Vm. Now Vm is cancelled. So finally I am getting only pi by root 2 into 2. Nothing but the 2 root 2. Okay, that is equal to 1.11. So this is the form factor of our waveform. Now let's see rectification factor. Okay, what is the rectification factor? 1 by form factor whole square. That is nothing but 1 by 1.11 whole square. When the form factor is 1.1, right? That is equal to 0.81. So this is the rectification factor. When compared to half wave, we are having more than the half wave rectifier. That is the very important thing. Okay, we need to understand. Okay, so now let's calculate the ripple factor of the output content. Voltage ripple. In this we have the ripple content, right? And output voltage. Now let's calculate this one. Output voltage ripple factor. That is equal to what? We know the ripple factor formula. That is nothing but root of form factor square by minus 1. We know the form factor is, what is the form factor? 1 point. So here I am getting the 1.1, right? 1.1 whole square minus 1. So that is equal to 0.48C. This is the voltage ripple content in our output waveform. So this is the our full wave bridge rectifier concept. If you want to design this full wave bridge rectifier practically, I provide the video link in description. In that video you will get the practical designing of full wave bridge rectifier by using MATLAB Simulink.